Hey, we in 3.1 still, functions, applications. This deals with gravity. It's probably like 93, 94. I had somebody ask just for part C. But 93, 94 is based on the height of an object. That is basically, you you have an object that's a certain height and it's thrown upward and then it comes back and hits the ground. So now part A and part B ask other questions, but what this little bit thing out here is represents like a building of some sort that is up on some kind of a ledge. Okay, and that ledge is represented by the height, which is h sub 0. Okay, when the object is released and it comes down, hits the ground, that g represents the gravity. Now that g can be different depending on which planet you're on. I think if you're on the Earth, I think that number is like 4.9. If you're on a planet that's a lot larger, like Jupiter, that's called the gravitational constant, and the gravitational constant is much bigger on a bigger planet because there's more mass, which has more gravity. And if you want to know a little bit more about that, ask Isaac Newton. So, but anyway, so this one right here is the height of an object, and excuse me, and it's on the Earth. It's because it's 4.9. Looks like the object is 60 feet before it's released. So this object is 60 feet high, or 60 meters. I think it's units actually meters. So it's 60 meters high, and it goes up, and it shoots back down and hits the ground. Now, part C is wanting to know when does the object hit the ground. Well, since h is representing the height, it hits the ground when h equals 0. So all you got to do is plug 0 in here, and you get 0 equals 60 minus 4.9 x squared. So it's not h of 0. That's a different. If you ask me what h of 0 is, you're basically telling me how high is the object before any time has gone by. And obviously that should be 60. Because if you put h of 0 in, it's going to be 60 minus 4.9 times 0 squared. Do the math, and it's 60. And that's how high the object is right here on the platform. Because no time has gone by. 1 second it might be right here, 2 seconds it might be right here, 3 seconds it might be right here. Don't know. Depends on it depends on the planet you're on. So, but anyway, then eventually, 3, 4, 5 seconds, it's going to eventually come back and hit the ground. Well, what they want to know is, what is that exact time? Is it 2 seconds? Is it 3 seconds? Or is it 4 seconds? What is it? And so what you do, you would solve this one here for x. And so we have, well, what I would do is I'd bring this number over here. And you got 4.9 x squared equals 60. And so then divide both sides by 4.9, get x squared equals 60 divided by 4.9. So back in, remember, early chapter 1, we was having a square root property. So 4.9 x squared equals 60 divided by 4.9, that's what you get. So then you take the square root. So if you want to know why did we have to do all that other preliminary stuff, is so we'll have some bases here. And so we can do these problems now. And now we know that everybody has seen these types of problems use the square root property. And now you should know how to do it. So x is equals to the square root of 60 over 4.9. You're like, well, isn't it technically plus or minus? Well, yeah, it is plus or minus, but the problem is you cannot have a negative time, because remember, x is representing the time. It's x seconds. So you cannot have a negative time. You're not Michael J. Fox, where you can go back in time, like come back to the future. If that was negative, it's actually referring to this right here. It's like a parabola going backwards. And so the time is 0 here. Release forward, that's forward time. That's backward time. And backward time would be have a time machine. So you what don't have the plus or minus is the negative you disregard. So that number right there, take the square root of 60 over 4.9, and I'm not sure what that is. I mean that number there's about 5, and 60 divided by 5 is about 12. So I'm guessing around 3 to 4 seconds. So I don't have a calculator on top right here. So, but when you take the square root of 60 over 4.9, my guess is probably around 3.3 seconds, maybe 3.4. I'm not sure. You'll have to do the math yourself. I might be off by a couple of tenths one way or the other. And but it should be around 3 to 4 seconds. So, but anyway, so that's when you got to understand, that's when the object is released and it comes back and hits the ground. Now, like I said a while ago, that number right there is going to change depending on which planet you're on. Of course, most of the time it's 4.9. We don't care what it really does in Jupiter and somewhere else. But but most number of times that 4.9. If that number is bigger, you're probably on a larger planet. If this number was like 2.8, 2.9, you're probably maybe on Venus or Mercury or somewhere like that. So, but the bigger the mass, the bigger that number is. And remember, that object right there is the height that it's released from. So if you're on a bigger tower, let's say the tower is 100 meters tall, then that becomes 100, but it's just that number becomes 100 instead of 60. But it works exactly the same. So, and of course, it'd probably take long. It would take longer for the object to come to the ground. Now, guys, understand this is all theoretical stuff. There's things that are not being thrown into play here. There's things like the wind and the object that you're throwing. Obviously, if you have something that has a very porous and stuff like that, or it would catch some of the wind on its way down, we're assuming it's like a shot that's not affected by the wind at all. So you got to remember there's variables that's not being thrown into play here. But this is all theoretical stuff. This is kind of like what it would be if it was a vacuum. So there's no air at all. There's no wind at all. But anyway, that's 93, 94 part C.